All right, thanks everyone. Our final speaker of the day will be Ronald Bitrate from Two Orioles. He's the founder of Two Orioles, and he'll be talking about high-performance AV1 coding with Eve and David. Thank you.
Thank you. So first of all, Nathan, Vittorio, thanks for organizing this. I think it's really awesome that we have an East Coast, a New York-based video conference. I've had a lot of fun here. My name is Ronald. Like you said, I'm the founder of a small video research company. We try to build video coding, so both encoder as well as decoder tools and products around that. And there's two of those that I want to talk about here today. First, dav1d, which is an open source AV1 decoder. And then later on, I'll spend some time going over a commercial AV1 encoder that we've developed internally, which is called Eve. But I'll start with dav1d. So dav1d is an open source decoder, an AV1 decoder. It's open source. It was released in September 2018 at the Videolan Developer Days in Paris. It's licensed under the very simple 2-clause BSD license. And it's maintained by a community of people using standard GitLab tools, IRC as communication, and it was sponsored by the Alliance for Open Media. Why did we do this? Why did we need a decoder? And I hope over the course of the day you've sort of see people make this case as for why we need a good decoder for AV1 is because what we had was just not good enough. Right? Everybody was talking about how AV1 is too slow, AV1 is too sluggish, libaom is a little bit big and difficult to work with. And we know that because we've seen that before with previous generations of codecs as well. And we like solving this by writing better decoders. That's what we've done before, and we decided we wanted to do that again. It's important, even if it's only for a little while. Right? Ultimately, we will all use hardware decoders, at least on our phones, but probably also on our laptops. But for the first couple of years, to jumpstart AV1 platform support, and to get people to get beyond this chicken and egg problem cycle, we need a good, fast, slim, well-trimmed AV1 decoder, and we were hoping dav1d would be that. So this is all words, right? So let's talk numbers. Right? Numbers are much better than words. So how fast is dav1d? In the first few slides, I'll try comparing it to libaom, and then later on, we'll start comparing it to other codecs as well. So in the first experiment, what I did is I used libaom to encode some 1080p clips. This is done at standard CRF values, so this is like at a quality that you would basically get from YouTube playback or things like that. And then we played them back using FFmpeg, either using its built-in AOM decoder or using a dav1d wrapper that is nowadays also integrated. And then we just measure how long did it take to decode that file, how many frames a second could it decode. And what you see is that in the clips that I've shown here, those were basically representative clips for either very easy content on the left, sort of mid-complexity content in the middle, or really highly complex content on the right. And in each of those cases, what you see is that dav1d is about twice as fast as libaom. But the frames per second numbers that you saw there are not enough to get real-time playback of 1080p, right? So if you want 1080p 60, that's not going to be enough. And we don't really get faster CPUs anymore, right? Clock speeds have sort of stopped going up. Nowadays, when we talk about computers getting bigger and better, what we're talking about is multi-core support. So you need threaded decoders, and you need decoders that can scale across many threads really well. So how does that work with dav1d? So dav1d is, I think, one of the first decoders that tries to use multiple threading models concurrently. So what you see in the graph here on the right is in red that libaom uses a very simple tiled threading model, which means that you just split an image up in two, and then one core will decode one half, and the other core will decode the other half, and voila, it's twice as fast. That's good. But the bit stream needs to support that, And at some point, that chunking of the file in equal sub-chunks, it sort of stops scaling. It doesn't really work anymore. So for this particular file, this file was encoded with 4 tiles. That means you can only get up to 4 threads to be active, and beyond that, it doesn't scale any further. It does scale well, though, right? So if you go from 1 to 2 threads, your FPS goes up on average over these files that I showed earlier, from 40 to about 70 FPS. Which is not that bad. And if you go to 4 threads, you get to almost 100 FPS. If you use dav1d with tile threading, the scalability is basically about the same, right? It's just that the base FPS is faster, and so it scales to a higher FPS also. So instead of going from 40 to 100, you go from like about 80 to 200. So it's still a 2x speed up. Now, in addition to that, dav1d also supports frame multithreading, which is where one core will decode one frame, and the other core will decode the other frame. And they can all use tile threading at the same time inside that process, so it adds up. And if you do that, then you see in the green line in this graph that it scales in pretty much the same way, right? So in and by itself, that wouldn't be very interesting. But if you add those two up together, it means you can get much better scalability, right? And so once we start thinking about, can I use this to do 4K playback, 4K 60 playback, the answer is that actually, yeah, you can. You can do that already. And at the end, if you use the multi-threaded configuration in dav1d, on my MacBook, it's about 3 times as fast as libaom, also in a multi-threaded configuration. But if you have a beefy machine, right, like you go to a 40-core Amazon machine, you can get up to 5 times faster AV1 playback if you use dav1d instead of libaom. So. But on my laptop, it's 3 times as fast. Okay, moving on. So playback speed is one thing, right? But it's also important that we're resource efficient, right? So beyond CPU usage, we want to look at things like memory usage and system load and things like that as well. So let's look at memory usage for a little bit. Right? Again, we have 2 threading models, so I want to sort of like look at each of them independently before we look at a combination of them. So the yellow line at the bottom is what happens when you enable tile threading in dav1d. And what you see is that memory usage doesn't go up at all, right? So the baseline memory usage of dav1d to play a 1080p file is about 50 megabytes, which is not that much. For libaom, it's a little bit higher, like 130 megabytes. And then when you enable tile threading, for dav1d, it's about flat. And for libaom, it goes up a little bit, but not that much. Frame threading, on the other hand, incurs a very significant memory penalty. So you need a lot more memory for each additional set of frame threads that you add to the pool. And there's an asterisk there, because up until today, this can blow up to like 500-600 MB for 16 frame threads on 1080p content. But Henrik actually prepared a patch which brings this down by 70%. So in a week or so, this will not be 600 megabytes anymore. This will be more like 200 megabytes. And that's very reasonable, right? At that point, you're right at the level where libaom was also. In practice, you will usually not actually use 16 frame threads. You will use like a combination of frame and tile threads, because as I showed in my previous slides, that scales much better and it leads to a much higher effective FPS. And if you do that, then with 4 frame and 4 tile threads, your memory usage at the moment is about 180 megabytes for a 1080p file. And with the work that Henrik is doing, that will probably go down to maybe 2/3 or half of that. Okay, then some other random numbers. Code size. I think it's important that a decoder is light and easy to maintain and easy to read. So in terms of code size, libaom's decoder, so that's for the code nerds out here, AV1/common and AV1/decoder, is about 74,000 lines of C code. And then if you look at the x86 subdirectories, there's another like 30,000 lines of intrinsics in assembly. dav1d, on the other hand, is only 32,000 lines of C code, and then another 37,500 lines of x86 assembly. Keep those numbers in mind. I'll come back to that in a little bit. But so essentially what you see is that it's just a lot smaller, and that reflects in the binary size. The binary size of a stripped libdavid binary is about 0.9 megabytes. And for libaom, that's 2.9, so it's 3 times as big. This is important if you want to ship the decoder in, say, an iPhone application or in a browser, right? The overhead of downloading each new version is just that much smaller. Okay, so Nathan asked me to get beefy and to get really down into the weeds. He said, you got to show these people how it works. Don't just tell them that it works. They don't care. They want to see how it works. So I'm going to show you guys how the inverse transform is implemented in assembly, and you're going to understand it, and it's going to be fun. You're going to understand it. It is going to be fun. Okay, so what is a transform, right? We need to start at the basics a little bit here. So a transform is basically to take away of hopefully spatially correlated values and then try to decorrelate them so that your signal is concentrated in just one of those numbers. So let's say that you have a 2x2 matrix of numbers, right? And that could be anything, but let's assume that they are pixels, right? And the simplest transform that I can explain is a Hadamard transform. A Hadamard transform simply means that you add 2 up and then you subtract the same 2 numbers also. So in this case, if I did a row transform, it means that I would add up the 4 and the 5, and then I would subtract the 5 from the 4, and that would be my 2 output numbers. And so if you do that for this matrix of numbers, then after the row transform, I have those intermediate 1D transformed numbers. I can then do a column transform also, which is, again, 9 plus 7, that's 60. 9 minus 7 is 2. And so you now see that I have spatially decorrelated values. I have one really big number and a bunch of really small numbers. And the video encoder will then quantize those, and the 2 and the minus 2 will probably go away, so you're probably left just with the 16. Then you have to run, as a video decoder, an inverse transform. And interestingly, for the Hadamard transform, the inverse transform is the same as the forward transform. So you just add those 2 numbers up. You have the 16 plus the 2. That makes 18. You have a scale factor of 2, so you divide it by 2. And you have 9. And that's the same number that you just had on top, right? And then you can do the same thing for the inverse transform for the rows again. So you have 9 and minus 1. And you add those up. And that's 8 with a scale factor of 2. And that gives you 4. That's the input number. So that's a transform, right? Very simple. So how does AV1 use transforms? AV1 has many, many transforms. So first of all, sizes. Let's talk about sizes, right? So a transform must have a horizontal and a vertical size because it's a 2-dimensional transform. So we can have any power of 2 size between 4 and 64. And those have to be in a 4:1 to 1:4 ratio. Then there is transform type. So in addition to a size, you can also have different types of transforms. I gave the example of the Hadamard, and in AV1 we use DCT or ADST or flip ADST or identity. Flip ADST is just the inverse of the ADST, and identity just means I did nothing. And DCT is the thing that we're all familiar with, or at least we try to pretend that we are. Then there's some rules over which sizes can use which types and things like that, and it's not really interesting. So in the end, you're left with 155 unique 2D transforms, right? That's a lot. And so as a video decoder developer, if you would try to write those out, that alone would take probably 5 megabytes, and that's too big, right? Because I want a 0.9 megabyte decoder. So the way that you solve that is that you just have uninlined 1-dimensional transforms. So I told you guys I'm going to show you code. So this is how libaom does the inverse transform, right? On top, you have essentially a function getter. Give me a function that can do a 1-dimensional column or 1-dimensional row transform. And then I just loop over each of the rows, and later on each of the columns, and I actually do that transform. And that's it, right? And in that case, you only have to implement 12 functions, plus 1 for lossless, but we're going to skip that. So this is how the C code gives you all of the inverse transforms in libaom. Moving on, assembly, right? How does libaom implement this in assembly? And the obvious answer is in exactly the same way. Or it's a little bit different. So in assembly, you cannot actually do a column transform. You can only do a row transform. So in order to do a column transform, you need to rotate the samples first. you transpose them. So you do a transpose, and then you call the row function, but it's really a column function that you called, and then you transpose again, and now it's like as if you call the row function. Then you call the column transform, you add the inverse transformed samples to your predictor, and voila, that was your inverse transform. So this is the function that I want to focus on because it's such a good prototype of why dav1d is faster in libaom and how dav1d is faster in libaom. Right? So first, let's look at how transpose is implemented in libaom. Right? And it's quasi-code, but the basic idea is there. So you load 16 samples from memory, because it's a 16 by 16, and each register holds 16 values. So that's 16 by 16 values. Then you rotate them, which is 64 instructions, and then you store them again, which is another 16 instructions. So 96 instructions to do one transpose, and we call that twice. Then, I told you that the row, because of the transpose, is the same as the column, 1D inverse DCT. So let's look at the IDCT16, the one-dimensional inverse DCT. Basically what it does is it loads a bunch of constants, which are the spec-defined way of doing the actual DCT. And then it does a bunch of multiplies and additions and shifts, and it doesn't really matter what they are, but they're spec provided, and there's a spec, so we're all good. And then before that, it loads the coefficients from memory, and after that, it stores the coefficients in memory. How many? And then there's a residual add, and I'm not going to talk about that. So how many instructions did the 1D IDCT take? So there's a prologue, which is 5 instructions. Then the loading of constants is 123 instructions. Loading of input, storing of output data, 16 instructions each. You need to put stuff on stack because you run out of registers, 43 instructions. And then the actual DCT, the actual transform itself, is 13 multiply cycles, which is 16 instructions each, to 208, and 24 sum add pairs, which is 48 instructions in total. And that's it. That's your 1D IDCT. So I want you now to compare these numbers to how dav1d does it. So dav1d doesn't actually use functions in the conventional C way, right? I sometimes smile a little bit when Nathan says that dav1d is really just a bunch of assembly with a thin C wrapper, but he's actually right. That's literally what it is. Because those are functions, you can call them, but they're not actually C functions. So there's no prologue. In fact, the calling convention of these functions is such that we make assumptions that stuff is already loaded in the correct AVX2 registers, so we never store anything in memory or load anything from memory. So there is no loading of input data, and there is no storing of output data. It is just already there. Because of the way that we load the constants, and because of the way that we interleave the loading of constants with the actual DCT transform itself, we can reduce that from 123 instructions to just 21, and we don't need to load anything from scratch or store anything from scratch. So that goes down from 43 to 12 instructions. And then the actual transform is actually almost the same, right? So the 24 by 2, there's no other way to do that. There's only one way to do addition and subtraction, so that's still 48. For the multiply pairs, we were able to simplify that a little bit, but it's still not that much. But in the end, if you add all of this up, you have a function that's only 242 instructions instead of 464, even though the function does the exact same thing. And it's just because we have a really weird calling convention, and we write it in really weird ways. So moving back to a two-dimensional DCT, then, how does that work? Well, it's basically just call this one-dimensional DCT twice, and then transpose, right? And the transpose is not 96 instructions, but 64, because we don't have to load from memory, we don't have to store to memory. Also, we don't call it twice, we just call it once, because we assume the input is already transposed, and that's free. So if you add all of that up, then you go to, for two-dimensional IDCT, you go from, what was it? 464 times 2 plus 96 times 2 instructions, plus a little bit to write it out. You go to 242 times 2 plus 64 times 1, plus a little bit to write it out. And in effect, that function will be exactly twice as fast. Now, did that make sense? I hope so. So I want to get back out of this rabbit hole, and if you fell asleep, I'm sorry, but you can wake up again. So the question that we tried to answer was, why is David faster than libaom, right? How can it be both faster and smaller? And the answer to that is, as we just explained, because we tried to write everything just a little bit differently. We tried to make things just a little bit more efficient, and I gave an example of one function, and we literally did that for every function in the specification until it was twice as fast. So we have better assembly. We have more assembly, right? If you think about the lines of code of assembly functions that I showed earlier, there was an odd thing there. Our assembly functions are half the size, yet the source code for the assembly is twice as big. That must mean that we somehow have more assembly coverage than libaom, and that's actually the case. So we have better assembly, we have more assembly, we have a lot of built-in code assumptions which make it really unsuitable for research, but really good as production code. And we have an interesting threading model, as I explained in the beginning, and I went more in depth in that in my talk at the Videolan Dev Days last year. So why is David so small and yet so fast? Now you know. It's because it's special. Okay, moving on. How does David compare to other codecs? And I sort of want to start with this quote, because I read this a couple of weeks ago, and that's quite a claim to make, right? So these guys claim that AV1 is going to be an order of magnitude more complex than all of these other codecs out there, and therefore you should not touch it. It's scary. Now the cool thing is we can actually measure that, right? We don't have to make claims, we can just measure it, and then we can see if it's true or not. So how do we do that? We are going to generate files using all these open source VP9, HEVC, H.264 encoders, and I decided to use CRFs so that we get a matching quality, so a matching PSNR, SIM, VMAF, whatever it is that you like, to the output quality of the AV1 file. And so in the list here, you can see which CRF values I used for each of these encoders to get a file that had a somewhat matching quality to the AV1 file, generated at the CRF value 44. And then we just used FFmpeg to decode these files and see how fast it was. And that looks like this. So on easy content, right, the one on the left, you can see that VP9 is in fact a lot faster than 264, and still 264 is a lot faster than HEVC and AV1. But interestingly, AV1 and HEVC are about as fast. Then for the more complex content, right, the mid-complexity in the middle and the very complex on the right, you can see that AV1 single-threaded is a little bit slower than HEVC, right? And on average, over all of the samples together, it's about 9%. And then VP9 is just a tad bit faster than H.264, and both of them are quite a bit faster than AV1. So the difference between AV1 decoding using David and 264 is single-threaded 34%, and VP9 43%. Moving on to the multi-threaded comparisons. First of all, David versus FFmpeg's HEVC decoder. Basically, the results are identical, whether it's single-threaded or multi-threaded. So single-threaded was 9% slower, multi-threaded is 11% slower, right? So that's not really a surprise. 264, really about the same. Single-threaded was 34% slower, multi-threaded is 38% slower. Then for VP9, something interesting happens. You see that it stops scaling. And if you paid attention to the earlier slide where I showed the frame threading results using David, you saw this exact same kink there also, where it just tapers off and it doesn't scale further than that. And the reason for that has to do with how entropy updates are cascaded between frames during the AV1 decoding process. And so at some point, that just gets stuck on itself, and you can't go any further. That mechanism is shared between VP9 and AV1, and so that same kink obviously shows up in both AV1 as well as VP9 decoding. The thing is, for AV1, we can use tile and frame threading to get around that. And for VP9, that unfortunately doesn't exist yet. So at the end of the day, even though VP9 is actually the fastest decoder out there, single-threaded, when you use multi-threading, you can see that the difference between VP9 and AV1 is suddenly very small, and it's only 20%, 21%. So it's not an order of magnitude, right? It's just 10 or 20% compared to HEVC or VP9, and that's very reasonable. Next, memory usage versus each of these decoders, and it's sort of all over the place, but in reality, it's all about the same, right? One of them uses like 170 megabytes, the other uses about 190 megabytes at 16 threads each. Honestly, it's a wash. It's all about the same. Okay. The last few things I want to talk about is portability and adoption. So first, portability. All of these experiments that I showed so far were done on 64-bit x86, Haswell supporting AVX2. For these systems, we have full assembly coverage and everything works great. That's what the whole thing was developed for. However, of all desktop and laptop users, that only covers 50% of the user market, according to online statistics, right? So the other 50% of the people have old machines. And we want to support those too. So David does include SSID3 optimizations, which basically covers over 95% of the desktop and laptop market user share. Assembly coverage is essentially complete. There's like 2 or 3 functions missing. And so even on these systems, David is a lot faster in libaom. Looking beyond x86, oh, and by the way, that works on 32-bit as well. Looking beyond x86, David supports and has significant assembly optimizations for ARM. Most of those are 64-bit only, but some of it also works on 32-bit ARM. Assembly coverage is 50%, and I think it was Thomas Davies that earlier said that the inverse transforms are about to be merged also, which will bring it up to 75%. I haven't done any actual performance measurements, but I'm just going to assume that it will be faster than libaom as well. Lastly, PPC. There is some ongoing work on VSX extensions, but there's not really that much to show yet. Then again, libaom only has one optimization for VSX, so you know, there's not much to show there yet. But work is ongoing, and if you are interested in tracking that, there is a bug report right there. Lastly, adoption. So why did we do this, right? We could have done this as a research project and then just shelf it and do nothing with it, but we really mean it when we say that we want to jumpstart the AV1 system, right? We want people to be able to start using AV1. We want websites to start streaming AV1. We want to consume AV1 because the video will look better, and eventually that means I can watch the best video out there, and that's what we do all of this for. So we were really excited when Firefox integrated David for their AV1 decoding, and in fact, they were kind enough to put out a blog post, not just saying, we have awesome AV1 support, but actually saying that is partially because of David. Thanks, guys. That's really nice. Chrome also uses David as a default AV1 decoder nowadays, and I believe we're included in things like VLC and FFmpeg also. So uptake has been really good. People have been really happy with it. I've heard David come up a couple of times in earlier talks today, so people seem happy with it. This is awesome. If you like any of this, it's a Videolan project. We are under the Videolan umbrella, and so if you want to financially support this, you can give donations to Videolan. There's a website there, and just in case you missed the donate button, it's right there. So for the second half of my talk, I want to talk about something that is unfortunately not open source, and that's Eve. So Eve is my company's encoder framework for writing software encoders. And I want to talk here about Eve AV1. So Eve was initially conceived as the basis for a VP9 encoder. And I put out a blog post about that a couple of years ago. Eve VP9 was released in 2016. And a couple of months ago, we released the first production-ready version of Eve AV1. Right? And just to be clear about who the target audience of Eve is intended for video-on-demand use cases. So this is not like low latency or live or things like that. This is all offline. We want it to be optimized not so much for metrics, but really for visual quality. We believe people should see the difference, not just measure it. It has production-grade rate control because people that use this tend to care about that. And it's a commercial product so that we can guarantee long-term support, long-term development, and the stability of the people behind it that work on this. So again, I like numbers, so let's just get straight to the numbers. how well does it do? So we can take a bunch of standardized 1080p clips, and we can encode that at a standard set of CRF values using a whole bunch of encoders, and then we can draw out bitrate versus quality, otherwise using kind of standard encode settings. And then typically you will get a graph that looks like this. Right? So on the horizontal axis, you have bitrate, logarithmic. On the vertical axis, you have an objective quality metric, in this case VMAF. And that means that if something is to the top left, it looked better at the same bitrate. So the blue line on top, that's AV1, and it does quite well, right? Then after AV1, you have one of the other, or two of the other encoders that I've tested, essentially overlapping for this particular file, for this particular clip. That's libaom as well as EVP9. And then after that, you have three lines that are, again, essentially overlapping just behind the other two. In yellow, libvpx. In brown, that was X265. And in green, SVT AV1, Intel's encoder that you heard about earlier today. And then all the way at the bottom, there is X264 and Ravi. Now, I know what you're thinking, right? Those are numbers. I don't believe that. So the people that are watching at home are not going to be able to see much of this because that video is compressed and compressed again, and so it's probably all going to look all over the place. But I hope the people in the room here can actually see and appreciate that there is an actual visible quality difference there. So on the left, you have a clip, in this case, Park Run, right? Park Joy. And it's encoded with libaom, and on the right you have that same clip encoded with AV1. And I shouldn't show screenshots. I should show actual videos. Right? The thing is that the visual difference is actually really quite stark. Right now, it has to be said, libaom does a lot of things good in this clip, right? If you look at the trees on top, the leaves for the trees, that actually looks quite decent on both sides. If you look at the people that are running around in the middle of this clip, it actually looks quite decent in both of these encodes, right? It's the grass at the bottom and the rocks at the bottom and the water at the bottom, where you sort of see the standard complaint that people have had about libaom and the previous generations for ages. It's so blurry. And then X264 is sometimes said to still be better than libaom, even though in the metrics that doesn't show up. And the interesting thing here is that that's not really true. Well, it's partially true. So if you look at the grass, it's actually true that X264 represents the grass in a much better way than libaom just did. The problem with X264, however, is that if you look at the people, that is quite something, right? And that's okay. I mean, so what you see here, and that's really interesting, is that the encoder is trying to make a trade-off between, do I want to preserve energy, or do I want to make other choices? And you can see that X264 goes a little bit further in one way, and libaom goes a little bit further in the other way, and it just leads to different types of artifacts. And then on the other hand, AV1 seems to do pretty well on both of them. So if you look at that graph that I showed earlier, you can look at the horizontal distance of two of those curves, or like a point on one curve, and then interpolate that as a point in the other curve. And that horizontal difference is then a bitrate difference. You can express that as a percentage, and then you can average that over the whole line or over the points of the line, and then you can average that over a whole point of clips. And that is the BD rate improvement, right? That's the percentage number that we always talk about. And really what we're trying to say there is, I needed 20.95% bits less than the other guy to encode at the same quality, right? So the difference between AV1 and libaom is actually 20.95%, 21%. You saw that EVP9 was sort of overlapping. It's a little bit behind, actually. It's like 26%. And then there were like 3 codecs after that were essentially grouped together, right? You had SVT AV1, which is at minus 34%. You had libvpx at minus 37% and X265 at minus 39%. And then at the bottom, you had the last 2 encoders, Ravi at minus 51% and X264 at minus 54%. So that's it, right? That's the quality difference. Now, I want to add a new variable there, runtime, right? Because as we saw in the talks earlier today, we don't actually care what the quality is. We care how long it took to encode, how long it took to get there also, right? What is the total cost of owning this media asset? The total cost picture is important, and encoding time is particularly important for that long tail of content that almost never gets viewed. So if you look at those numbers, you will see that, yeah, AV1 may be the best in quality, but it's actually really slow also. In fact, it's 100 times as slow as X264 in this particular set. But that's the thing, right? We can change the speed preset. We can go from very slow. We can go to very fast. We can go from, and we can do that for each of these encoders. So let's compact all of this together and call this one data point, and then do this for all of these encoders at all of the speed settings. And what you get then looks like this, right? So this is like we just zoomed out, like a whole dimension. And what you see in the horizontal axis is what Thomas Davies earlier showed on his vertical axis is the encoding runtime. It's, again, logarithmic, and so left is very fast, right is very slow. And then on the vertical axis, you see the bitrate reduction, right? Where top means the reference point, like the best quality, and further to the bottom means that you need more bits to represent the same quality. So in the dark blue, you see AV1. And as the speed settings go up, it does actually get significantly faster. And as you would expect, the quality drops a little bit also, because these are not FPGAs. This is a software encoder. In red, you have libaom. And in that same sort of like bucket on the right, you have all of the other AV1 encoders. So you have SVT AV1 in green, and in brown, you have RAVI. And there's like a 10–20% difference between each of these. And so what that tells you is that you can get higher speeds, but it will cost you quality. Then further to the left, you have X265 and the VPX, which, as we said earlier, essentially overlap, although X265 can go much faster than libVPX, the high-speed presets, and X264 all the way on the left. So the conclusions here are that if you care about very high-speed encoding, there are encoders and speed presets out there that can do that. And in fact, AV1 appears to already have multiple, as you've heard today, that can do that. We're definitely working on getting there too, but we're apparently not quite as far as some of the other encoders yet. Then next, what about multithreading, right? So one way of speeding it up is use a higher speed preset. The other way of speeding it up is just use more cores. So in order to look at that, I decided to look just at the AV1 encoders here. And I looked at the second speed preset. Why? Because they seemed nicely horizontally aligned. So it sort of starts at the same point, right? And then instead of looking at different speed presets, we look at different threading configurations, right? So 1 thread, 2 thread, 4 threads, and so on. And if you do that, the results look essentially like this. This scales a lot better, so the quality loss is a lot lower as the speed goes up. But there's still some quality loss associated with enabling threading in each of these encoders, except for SVT AV1, which is very interesting. So no matter how many threads you use in that encoder, the result is almost identical, which is really quite good. For each of the other encoders, it's actually easier if you take its own single-threaded point as a 0 point, so you make it look like this. And then what you see is on the horizontal axis for relative speed up, you can see that RAVI on a 16-core machine with 32 threads can be about 13–14 times faster than single-threaded. And that's pretty impressive. Unfortunately, it does cost a lot in terms of quality. It goes down by 12%. libaom just doesn't scale as well, and it seems to be like a general pattern, right? When we went to higher speed presets, it didn't really scale at the very high end either, and it only gets a 6x speed up in the same threading configuration as RAVI. On the other hand, the quality loss is only 6%. AV1 can scale same way as RAVI, so 13–14x for a quality loss of 4%. And for me, the impressive result here was that SVT AV1 actually scales to 15.5 times, and there's no quality loss. That's cool stuff, right? There's a baseline quality thing that still has to be addressed there, but their multi-threading is really good, and I like that. I'm going to look at that. So take-home lessons, right? What can you take home from this? the question I think that we're all asking is, can I start using AV1? Can I start deploying AV1? Can I stream AV1 to people? And which part of the tail, which proportion of my users can use that? Right? Ultimately, from an end user point of view, AV1 provides very good quality versus bitrate trade-offs, better than libaom. AV1 also gives better absolute speed versus quality trade-offs than libaom. And in a relative sense, SVT AV1 actually scales much better than libaom also. Lastly, multithreading, all of the encoders appear to scale better than libaom. So the funny conclusion is that it turns out that libaom is really nice, well-written reference software, and it's a good baseline. But unlike HM, which is sort of like this theoretical limit, libaom is a baseline. And you see that each of these encoders try to jump above that and go beyond what libaom has done so far. And we saw that in earlier talks from Thomas, and we saw that in the NG codec talk, and we saw that in all of these talks that we can do better than libaom. And it's really exciting to see how everybody's taking that in different directions. Right? And all of these projects are still moving. You can see how we're improving over each month. And I think it's really exciting to see where this will go. So should you use AV1? Can you use AV1? I guess my sort of like hand-wringing answer is, if you want x264 preset as medium, then no. If you're okay with slower, then there's probably an answer to that. Yes, you can probably do that. Right? In the end, it comes down to just pick a good speed preset, and the results that I showed suggest that at that point it's actually more effective. And at that point, it's just a question of, does your target device support it? And with that, I'll be taking questions.
Thank you so much, Ronald. I'm sure we have lots of questions for Ronald. We have a few in the chat. I just want to bring some more from the room as well, too. The first question from the chat that we got was around David. So how have you kept the downclocking effect caused by AVX2 in check when David is used as part of other stacks?
So the answer is that we don't really have any control over that, right? So because AVX2 is used, the whole thing will be downclocked, and that will affect the whole system. I think that the answer to that is not to try to reduce the downclocking, but just to accept that we're all going to have to write everything in AVX2, and then it's not an issue anymore.
Great. And from Oliver down here.
I want to thank everyone that's been working on David. I think it's doing a huge impact to the AV1 community, and so really happy and congrats on all of that. My quick question is, have you looked at a David implementation targeting WebAssembly, specifically for Safari?
I believe Brian has actually worked on that, right? He has, so you should definitely talk to him.
It works, but it's slow.
It works, but it's slow, he says. But so he actually showed some work on that in the chat, and I don't want to preempt anything that you don't want to disclose yet, but
it gets faster in the future.
It will get faster in the future, he says. So it's ongoing.
Yeah, it seems like a common theme with today. Everything is improving, and this is all just part of the step in the process of AV1.
Right.
Does anybody have any other questions in the room? Oh, there's one over here, and one in the front as well, too.
So the pre-AVX computers, how much is that share is from stuff like Atom, and how much is it from old computers, or both?
You mean the SSSE3?
Yeah.
And sorry, what was your question?
How much of it's from the user base for that is from Atom, and how much of that?
The user base. I honestly don't know. I think it's sort of like a long tail, so it's not like one specific class of systems. We're trying to group it by like what proportion supports this particular instruction set, but it's very heterogeneous. So it's all kind of people using all kind of weird systems.
Yeah.
So I don't have a specific answer for how many people use Atom.
I just asked because the code tends to perform differently depending
yes.
on what.
Yeah, that's absolutely true. So I think that for other decoders that I've written in the past, we did try to address that, like loading GPRs well before you access them to load XMM data and things like that. But those are typically things that we sort of did like at the end. So we first tried to get high assembly coverage, and then later on we'll optimize the assembly for like one particular sub CPU, if that makes sense.
Oh yeah, I have a question. So you mentioned that the David's performance is only 30% worse than VP9 or software decoder, right?
Yes.
And because from my most recent test on VP9, even if software decoding, it's probably using on the 2-core, 4 hyperthread, 3 gigahertz computer, not the greatest computer, but also not a very bad. It's kind of using 20 to 25% of CPU. That's at least what I mentioned, what I measure on my laptop. And so if that's the case, if what you said is true, David can already provide a software decoding solution for a lot of...
Yes.
Okay, so do you have any data published
On
like testing David on a bunch of different CPU or GPU SKUs and see the CPU usage?
Right. So no, we haven't done any specific tests on that. I think the way that I look at that is that from my personal interest, it's a little bit out of scope of what I personally would prefer to spend most of my time on, right? So I can divide my time between measuring things or just writing things, and to measure it over a very large group of CPUs is not something that I personally do. Now, AV1d has been doing a lot of tests, and so AV1d has been doing a lot of tests, measuring David performance on different systems in different threading configurations. And so I would try to hit him up and see.
My real
if he has an
question is,
opinion on that.
do you believe David is already good enough?
Yes.
Okay, so...
Yes, I believe that David is good enough.
All right, did we have any more questions? Any more questions for Ronald? All right, well, if everybody could thank Ronald for being here as well, too. And that